Welcome to my talk on lightweight kernel isolation with virtualization and VM functions, an approach to isolate device drivers inside the Linux kernel. This is a joint work between University of California at Irvine and Penn State University. Operating system kernels, they are everywhere. They power millions of devices ranging from smartphones to autonomous cars to home automation devices. Not all devices are built with security in mind, thus they are prone to attacks. Here's a graph that shows that hundreds of vulnerabilities are reported every year in the de facto commodity kernel Linux. Why? Because kernels are complicated and have a huge code base. For example, a recent version of the Linux has more than 17 million lines of code spanning across numerous subsystems with more than 8,000 drivers. Though the core part of the kernel is relatively stable, the number of device drivers are growing every day. Moreover, Linux is developed across the globe by thousands of developers. Often device drivers are developed by third-party vendors. Not all of them have a complete understanding of the kernel interfaces or the security idioms, thus resulting in a steady stream of errors. Modern systems are catching up. They do come with a lot of defense mechanisms in both hardware and software. For example, Linux kernel is equipped with address space layout randomization, stack canaries, data execution prevention, and so on. These are good enough for preventing trivial forms of attacks such as stack smashing or code reuse attacks. However, they don't seem to be enough to protect against all the vulnerabilities. For instance, if we assume that the control flow is completely secured using a mechanism such as code pointer integrity, it could be attacked using a data-only attack. And automated attack generation tools make these trivially possible. Let's see why kernels remain vulnerable. Commodity kernels, often for performance reasons, run the core kernel and all of its subsystems in a single address space in a monolithic fashion, where a vulnerability in a single subsystem could potentially compromise the entire kernel. A natural solution would be to isolate kernel subsystems such that a vulnerability in a single component, say a device driver, is contained within itself. However, isolation comes with a lot of challenges. First, it's the complexity of the kernel. It's hard to cut through a massive monolithic code base which is not intended for isolation. In one of our previous work, LXDs, we define a set of tools, including an interface definition language and a compiler, which automatically generates glue code to run parts of code under isolation inside the Linux kernel. The second challenge is the lack of fine-grained isolation mechanisms in hardware with low overhead. Let's look at the hardware isolation mechanisms we have. For decades, x86 provided us with only two hardware isolation mechanisms, namely segmentation and paging. Though segmentation has a very low overhead of 50 cycles, it is deprecated in 64-bit hardware. A well-optimized domain crossing implemented using a page table switching would cost 1,000 cycles. This number comes from the fastest microkernel SEL4. However, things are changing. Hardware is catching up and trying to introduce new isolation mechanisms. Recent Intel CPUs are equipped with two fine-grained hardware isolation mechanisms, namely memory protection keys and EPT switching. Let's take a look at those. With the 4-bit key inside a page table entry, MPK provides fine-grained isolation within an address space with an extremely low overhead of 20 to 26 cycles. However, this solution is not aimed for kernel isolation, as it works only on user-accessible pages. It could be feasible to use this for kernel isolation with additional security measures, but MPK calls for drastic security measures such as rewriting all the binaries and libraries in the system to prevent a particular instruction sequence, write PKRU, which makes it an impractical solution for kernel isolation. The next is EPT switching. The software running inside a VMX non-root environment can switch the root of its page table pointer with the set of pre-configured page table pointers, thereby switching the view of memory from one to another with a single instruction without exiting into the hypervisor. The overhead of this VMFUNC instruction is in the order of 100 to 150 cycles, which is comparable to a syscall overhead of 150 cycles. However, this solution requires a hypervisor. It is very important to note that neither MPK nor EPT switching provides native support for kernel code isolation. With lightweight virtualization domains, we introduce new mechanisms to use EPT switching for kernel code isolation. Let's take a look at what an EPT is. A software running inside a VMX non-root environment can have its own page table called the guest page tables, which translate a guest virtual address to a guest physical address. However, the guest physical address is not physically contiguous, so we need a second level of translation tables to translate guest physical address to host physical address, which are defined by the extended page table. Let's take a closer look at the VMFUNC instruction. Here we have two domains, domain I and domain J, which are backed up by EPT-I and EPT-J respectively. They run in the non-root VMX environment. Here the domain I executes a VMFUNC instruction. The hardware checks the EPTB list and switches the view of memory from EPT-I to EPT-J. Yes, it is really that simple. VMFUNC just switches the view of memory from one to another without changing any of the registers. In here, even the program counter and stack pointer would remain the same. So in order for this mechanism to work, the code page containing the VMFUNC instruction should be mapped onto the same virtual address in both EPT-I and EPT-J. Moreover, to run code inside the EPT-J domain, we need to have a valid stack. Let's look at the LVD's architecture. Here's a non-isolated system. Since we want to use EPT switching as our mechanism, we need to introduce a thin, lightweight hypervisor into the Linux kernel. By inserting a module, this hypervisor deprivileges the entire system. We create an EPT for the deprivileged system where we map all the memory one-to-one onto this EPT. We call this EPT EPT kernel. To create an isolated domain, we create an EPT called EPT isolated. Since we want to run unmodified device driver under the isolated domain, we make use of our IDL compiler to automatically generate the stub driver, trampoline functions, and the glue code. The stub driver acts as a proxy for the driver running inside the isolated domain. Let's take a look at how a network packet send looks like in our architecture. An user application that wishes to send a network packet drops into the kernel using a system call and eventually passes through a series of networking stack and finally reaches the stub driver. The stub driver marshals all the arguments and calls into the VMFUNC trampoline. Before calling into the VMFUNC trampoline, it selects a stack to run code inside the isolated domain. Once the VMFUNC instruction is executed, the view of memory changes and the control is handed over to the glue code. The glue code unmarshals all the arguments and eventually calls the appropriate function. In this case, it is packet transmission, and then the packet is queued onto the hardware. This looks pretty straightforward in the views of a developer. Let's pause for a moment and think of it like an attacker and see what attacks could be mounted against this architecture. Since we don't trust the code inside the isolated domain, an attacker could take over the control flow and jump into the middle of an instruction that could be interpreted by the CPU as VMFUNC, thus escaping the isolation boundary and could possibly execute arbitrary functions inside the Linux kernel. To prevent this attack, we carefully design the address spaces such that the virtual addresses of isolated domains, kernel, and the user processes do not overlap. If you look at the picture here, the LVD address space do not overlap with the kernel address space or the application address space. Since the code inside a VMX non-root environment can manipulate its own page tables, we need to restrict that from happening. To make that, one could map all the page table pages as read-only inside the EPT. However, this would cause frequent frequent exits into the hypervisor as the hardware would update the accessed and dirty bits onto these entries. Instead of this, we map all the page table pages as read-only inside the guest page table. Since we run the isolated code under ring 0, a malicious domain can possibly execute sensitive hardware instructions such as manipulating the control registers. So we trap into the hypervisor on all sensitive instruction accesses. Typically, stores to control registers, accesses to MSRs and IO ports, debug registers, and descriptor table registers. In all of these accesses, we drop into the hypervisor and emulate the instruction if it is coming from the kernel domain. If it is not coming from the kernel domain, we send an upcall to the kernel to terminate the isolated domain. It is not just the sensitive instructions. When transitioning back from an isolated domain, we cannot trust any of the register state. For example, let's consider this scenario. An attacker populates the global segment register with a bad pointer before returning to the kernel. If we don't sanitize or restore the global segment register properly, which is used by the kernel for per CPU variable accesses, we would eventually crash the kernel. To prevent this from happening, we create a per CPU VMFUNC state page where we save all the register before transitioning into the isolated domain and restore it on the way back. We have seen the attacks now. So let's see how interrupts are handled inside our LBD's architecture. Since we run isolated code in ring 0, we need a safe mechanism to handle interrupts. One naive way to handle interrupts is to drop into the hypervisor, but that would cause severe performance overheads. Instead, we carefully design an exitless interrupt scheme where we map the IDT and the interrupt handler trampoline in both EPT kernel and isolated. When an interrupt is delivered, the hardware pushes the trap frame onto the kernel stack and starts to execute the interrupt handler trampoline. Inside the trampoline, we consult the VMFUNC state page where we have a variable that says whether we are running in the kernel domain or in the isolated domain. If we are running in the isolated domain, we transition back to the kernel domain and continue execution. Then we switch the stack to a dedicated kernel stack and process the interrupt handler. Once we are done processing the interrupt, we return to the appropriate domain. However, this architecture could be trivially attacked. Consider this: an isolated domain. Inside the isolated domain, an attacker configures the stack pointer to point to a bogus value and then spins in a loop and waits for an interrupt to arrive. Once an interrupt happens, the hardware would push the trap frame onto this bogus pointer, resulting in a panic of the entire system. To prevent this attack from happening, we need a mechanism to make sure that interrupt handlers are always run on a valid stack. To achieve this, we make use of a hardware mechanism called interrupt stack table, with which we can configure the interrupt handler to always switch to a well-defined stack. This mechanism prevents the interrupt attack. Now that we have seen the architecture, let's see how much performance overhead we introduce. When we exit into the hypervisor on sensitive register accesses, we encounter a performance overhead of 1200 cycles that is exiting into the hypervisor. In interrupt handling, for a vanilla Linux kernel, it takes 600 cycles for processing an interrupt. When run on top of a hypervisor, it introduces a minimal overhead of 10 to 20 cycles. In the LVD kernel, we are switching to IST stacks and switching back. That causes an overhead of 50 to 60 cycles compared to the vanilla Linux kernel. And when we run on top of a hypervisor, LVD kernel has a comparable overhead compared to the vanilla Linux kernel in the order of 10 to 20 cycles. When an interrupt is delivered inside the isolated domain, we pay an additional overhead of 2 VMFUNC instructions, that is 400 cycles. Having seen the overheads at a micro level, in terms of interrupt delivery and exiting into the hypervisor, let's see how this translates to the system as a whole. So to measure the overheads of virtualization, we ran whole system benchmarks using Phoronix test suite. We ran a set of system-level benchmarks in which Apache Nginx dbench and sysbench experienced 2 to 5% overhead. And these overheads are caused due to exits into the hypervisor. And many of the exits are due to accessing these two MSRs, that is programming the APIC timer and accessing the FS base during a context switch. The remaining benchmarks are within 1% overhead of the non-virtualized system. To understand the overheads of isolation, we do several case studies. In the first one, we study a software-only device driver, for example, a dummy network driver and a null block driver. These are device drivers that represent a device with unlimited bandwidth and is not backed up by any hardware. By studying these drivers, we can understand the overheads of isolation better. Our system setup is based on Cloud Lab infrastructure. We run a 2-socket Intel Xeon 10-core CPU at 2.6 gigahertz with no hyperthreading. We run all our benchmarks on top of Linux version 4.8.4. Our setup is available for experimentation at the following link. One could click this link and instantiate a couple of nodes which are pre-configured to run our experiment. We run iPerf benchmark and measure the transmission I/O operations per second on 2 different configurations of the dummy network driver, that is native and isolated. We vary the number of application threads from 1 to 20. In a single threaded case, native is able to push out a packet in 2680 cycles. Whereas our isolated, in isolated, we pay an extra overhead of 280 cycles for domain switching. For 20 threads, we achieve 88% of the native performance. Typically, a network packet send involves two domain crossings. One is to send the packet and the other one is to free the packet. In that particular setting, we achieve 72% of the native performance. In the second case study, we study a hardware device driver, specifically an Intel 82599 10 gigabit Ethernet driver. We run iPerf benchmarks and measure the transmission bandwidth in both native and isolated setting. In a single threaded case, isolated is 5% slower compared to the native. And for 2 to 20 application threads, we are on par with the native performance. To conclude, with the availability of new hardware mechanisms, fine-grained isolation within the kernel code is possible. With LVDs, we define new mechanisms to isolate device drivers inside the Linux kernel by leveraging hardware-assisted virtualization and EPT switching. The source code for LVDs is available at the following link, marsresearch.github.io/LVDs. Thank you for listening to my talk.